this. So exercise number 11 was for a quiz. So the question was, what's the probability to get a queen? Well, to get a queen out of a deck of 52 cards, we had 4 queens, if that's a fair deck. And of course, this should be simplified, so we can write it as a 1 out of 13, or we just get this calculator and divide 1 by 13, or you could also divide 4 by 52. The result be same, and it's equal to 0.0769, etc. So it looks like pretty much everyone did this correctly, and that made me very happy. So it looks like you know how to produce those fractions that correspond to probabilities. So now problems start to get a little bit more challenging, and that's what I was about to do. So that's great that you want to take a look at problem number 21, because in this situation, they actually show the 4 possibilities or so-called outcomes that you produce when flip a coin 2 times. So in exercise number, so this was problem number 11. So problem number 21, that we had to find a probability to get 2 heads. And to get 2 heads out of total, so we always put total in our denominator. So in this case, looks like there are 4 possibilities. So there is 1 out of these 4 that is exactly what we need, 2 heads. So it's 1 out of 4, or 0.25. So this is how we get this probabilities calculated. And one can say, Alex, should I put 0.25 or leave it as a quarter? Well, that's the same thing. So probably in the back of the book, they have 0.25 or maybe a quarter, because those are 2 exactly the same numbers. So to me, it doesn't really matter. As long as you put your fraction in the lowest terms, then you're fine. So let's do some more. And before moving on, I'd like to clarify this little experiment that talks about taking a coin that has 2 sides. On one side, we have a head. On the other side, we have a tail. And you can flip it once, so there'll be either a head or a tail. Or you can also flip it once again, and guess what? It's also going to be either head or tail. So what I'm doing right now is producing a little so-called tree diagram to list all of the possible outcomes. That's how they call them, statistical word, outcomes of this particular experiment. And there are 2 of them, either head or a tail. But when you do it once again, then notice that if I go along the branches of this tree, I will get either 2 heads, and that's exactly what they had here on the first position. Or if you sink down, so you start with a head and then go down to the tail, then you go tail and head, and also tail and the tail. So you have 4 possibilities, and you just need to get out of 4 whatever fits description. So you can see that there was 1 with 2 heads. So it's always nice when you can list all of so-called outcomes, because this way you get intuition into what is going on. So I'm going to flip the page and do some more problems on these probabilities, because it turns out that from now and on, probability will always be with us, and in chapter 11, as well as in the next chapter, in the chapter 12. So let's try exercise that should be somewhat familiar already with this little cube, the die. Remember, we had these problems last time. So this little cube has 3 sides, and when I rolled it once, I could get either 1 or 2 or 3 or 4 or 5 or 6. So in a group of exercises next to it, they're talking about rolling it twice. Or if we had 2 dice and just throw it once. It doesn't really matter because it looks like it's be pretty much the same exact situation. And what they do is list all of the possibilities. So it turns out there are 6 choices or 6 outcomes that you can get on the first, right? You can get either 1 or 2 or 3, 4, 5, and 6. So there are 6 possibilities. And also there are 6 possibilities for the second. So if I roll 1 and, which means times the other, the total will be 6 times 6, which is 36. And that's exactly what they listed in here. So you can see that when your first die has 1 on it, so notice my first row goes with all of the ones. So if you get 1 on your first die, you could get any of 6 possibilities on the second. 1, 2, 3, 4, 5, 6. So you can get any of the 6 on the second. But you can get 2, and that will correspond to the next row, to the second row. And again, you're going to have all of these 6 possibilities from 1 through 6 here. So that's the second row. Then you can get 3, you can get 4, you can get 5, and you can get 6. So nowadays there will be 6 with each of those, right? So you have 6 once, twice, 3, 4, etc. 6 times 6. And they listed all of them. And that's great because once you have it all listed, then you can definitely do those problems pretty straightforward way. You just need to pick some number or whatever fits your description and divide by 36, because looks like our total here is 36 for this group of exercises. So why don't I try with problem number 35 and see how we can answer question in here in 35 that says, find the probability of getting 2 even numbers. Probability that we have even number and another even. Well, what does that mean? I think we already saw this once a while ago when we looked at all of the evens when we roll the die once. Those will be 3 choices. 3 choices out of those 6. So it'll be 1/2, right? Probability to get even is 3 out of 6 because 3 evens out of 6. When I say, well, now it's getting a little bit harder because we have 36. So we're going to have 36 in denominator. So which ones will correspond to 2 evens? Well, looks like nothing in the first row. There'll be 1, 2, 3 in the next row, right? Nothing in the next row because it has 3, it's odd number. And then I have another 3 in the next row, right? And then I have another 3 in the last row. So what is this equal to? Well, looks like we have 3 and 3 and 3, so there'll be 9 out of 36, which is exactly 1/4, 1/4, right? So a quarter of possibilities happen to be here. Just look at them. In the first row, I cannot select anything because I need both evens. And the first is 1, so it's not working. In the second row, I also have 3, so it's not possible to get both evens. Same with the fifth row, because I also have odd number 5 there everywhere. So I just use rows 2, 4, and 6 and get that result. Well, I can say, Alex, that's pretty tedious to list all that. And the answer is yes. Yes, it turns out you could solve this problem algebraically without any listing. You could utilize the fact that end means multiply times, and you will multiply 1/2 by another half. Why do you multiply 1/2? Well, because we just saw that probability of even is 1/2. And notice if you multiply 1/2 by 1/2, you're gonna get 1/4. The same exact thing. And that's not the way that we did the problem using all of those outcomes. I just did it formula way. I multiplied 2 fractions and I produced the answer. I say, so Alex, you did the problem 2 ways. Which way should I do it? It doesn't matter to me. As long as you do it right, it's fine. So some people prefer to do it shorter using the formula way, but some people like to do problems intuitively, so you can better see what is really going on behind the scenes on this exercise. So that's why I would say it is really your decision that how you do this problem. And that's interesting to realize, actually. So for exercises that have samples, or they say sample space, nicely listed for you, of course, it's much more straightforward to do the problem intuitively. So just see out of this 36, how many elements will be of your interest. But if they didn't list the sample space, well, then I would just use the formula and that'd be great. So let me try one more, like problem number 38 here. That says the two numbers whose sum is 6. So what are they really talking about? 38. Well, please notice that if I look at the first row, then 1 plus 5 will give me 6. So that's the selection. In the second row, the sum 6 will be when I add 2 and 4. I say, Alex, looks like if you go along this diagonal, 3 and 3, and then down to 4 and 2, and then finally 5 and 1, and that will give you the answer, right? So we can say probability that sum is 6. We're going to have out of 36 total possibilities, 5. So looks like this kind of question you cannot answer using formula. You have to list all of your sample pairs, and then you will right away see what the answer actually stands for. So it looks like some problems you just do directly, and I guess that's what we should get used to. So let us try another one, like 39, the one right next to it. I think that'd be another good practice exercise. So it says two numbers whose sum exceeds 12. So what are they talking about in 39? So probability that sum exceeds more, right? than 12. That's what exceeds means. So what numbers are more than 12? 13, 14, 15, 16. Can we see any numbers here that I can add and get something more than 12? When you say, Alex, the biggest one I can get is add 6 and 6, and this will be 12, but that's not going to exceed 12. Okay, so out of 36, how many do you see that exceed 12? I see none of them. I see 0 of them. So the answer will be 0, just like that. So the answer is 0. Remember, it is possible. When you say, Alex, I want to roll this dice and I want to get a million. You say, just forget it. You cannot get a million. Same thing here. You cannot get more than 12. 12 is the largest. And that's it. So looks like we get fractions. So denominator is always our total. And for a numerator, we get that whatever number of selections we're interested in. So let's try one more. So the goal here is just to do some problems and get used to this a little by little. So let me look at the next side of this page and try exercise like 49. So this talks about some kind of sickle cell anemia, and that's a disease that people inherit. That's pretty sad. So the point of story that they have a little bit of information here, and notice that we have a little table analogous to the case with the head and tail. So there is either capital S or lowercase s, and with capital S, there could be either capital or lowercase, and same with a little s, either capital S or lowercase. So same exact tree diagram, but now we have, instead of head and tail, the capital S and little s, right? So those are the ones. Okay, so looks like it's familiar, but they just put this in a table. Okay, so looks like there are two parents, and parent has either capital S or little s, and then second parent also. So there could be both S or both little ones, or one big and one small. So what do they want? Well, they want to find the probability that someone has that disease. So we need to read and see what does that mean that we have that someone has that disease. So they say if we use a little s to present a sickle cell, and S is a healthy cell. Okay, so looks like the illness will be produced in what case? So find the probability that there is a parents that has a child who has sickle cell anemia. So the question is, in what situation this sickness appears? Looks like there is lots of technical information, but the question is two. So there are two. There were children of the two S and little s parents. So the question is, what's the case when somebody has the particular disease? So looks like this exercise is not very clearly given, because if they ask in exercise 49, what's the probability that someone has that particular disease? The question is, what out of 4 are they interested in? Is that going to be both little s? Is that what they mean? Or what? So probably, right? Because this is something that
Professor, is not like if you
don't
carry
really
the gene.
clearly say. So this kind of problems are definitely not going to be given on the exams. So I think that little s and little s is what they're interested in. And looks like out of 4 possibilities, let's say, what are the 4? Well, here's first, here's second, here's third, and here's fourth. There'll be only one that has that disease. So it's a quarter or 25%. So I guess the person has that illness if both those are little s, no capital S. But again, it's not very clearly stated. So I guess that's not probably a very good example for the exam. But it's not very hard to solve, right? So you have total 4, and you see how many out of total is what you're interested in. So what about if you try exercise for a little quiz? Like a problem very similar to what I just did here in the table related to previous problem. So how about if you try to find exercise number 37? Answer. And I would say it's very, very similar. Oh, sorry, 36. 36. I just highlighted 36 and put 37 for some reason. So it is very, very similar to problem number 35 that I just did. So you can look at exercise 35 and, well, kind of repeat all was done in that little problem.